Okay.帮我关个后面的门吧，谢谢，免得吵到罗老师。谢谢啦。Okay, so let's share it. Okay, so let's continue our lecture. So suppose I guess we can finish chapter 3 in next week. All right, next week, I believe. And then suppose we will have our midterm 1 next week. Yeah, I suppose. So we need to be prepared, okay? And yeah, that's it. So last time we talked about the torsion formula. Last time, the most important thing is this one, all right? The torsion formula, which connecting tau and the T, all right? Just like sigma and the P, right? And the proof in mechanics of material, typically using the stress times the area, and then maybe sum it up together or do the force balance or moment balance, and you can get your result. Okay, 95%, more than 95% of the proof in mechanics of material. All right, just like this. And then during the proof, we noticed that we need to introduce one new terminology called moment of inertia. Moment of inertia has several meaning. I mean, well, one important concept is that how difficult of that section rotate about either a point or an axis. Okay, so in this case, it rotates about a point or about the axis penetrating from you to the monitor. All right, so it rotates about the actual axis of this bar, right? So it's called polar because the rotation is at the coordinate of the polar coordination. All right, and then if the rotation is simply rotate about axis like x or y, and you will have ix or iy. The x is the axis you rotated about. All right, and the value of the moment of inertia can be found in appendix what? D, maybe appendix D. Yes. So appendix D, you can see that it will provide several shape of this, and then you have many values here, and each of them has their own axis. And you can notice that all the rotation about the centroid will always be the minimum. It's a minimum, okay? Centroid, the axial axis through the centroid are always minimum, okay? Well, it's easier for it to rotate about its centroid. For other axis, rotation axis, it will always make it harder and harder, or difficult, more difficult and more difficult, more and more difficult. All right. So that's the concept. And then after we combine the theta and tau and torsion formula and Hooke's law, and we found that phi equal to TL divided by GIP. This is quite typical. And the limitation is that because our proof is based on a circular cross-section, so yes, you cannot apply to the square. And then this example, just applying the formula And then you can notice that tube has more efficiency compared to the solid one. Okay, next one. Well, the rest of part of this chapter will be quite quick or quite fast because you have done that already. You know the concept already because it's all similar to axial loaded member. You can see that non-uniform torsion and different cross-section, very similar to what we learned in chapter 2, right? So for example, you have T1, T2, and T3, or T4. Okay, so you have complicated torsion. It's not pure torsion anymore. Okay, and you don't have the pure prismatic bar anymore. Instead of that, you have different cross-section. But don't worry, you know how to do that, right? Because when you are going to take a look or to determine the internal torsion in one section, all you need to do, just cut it, right? Cut it. So you cut it and leave the left-hand side. Okay, so this is the first, leave the left-hand side, and then you can see that if you leave the left-hand side, you have T3, of course, T2, of course, and T1, of course. And your TCD is the torsion, internal torsion in between LCD, length CD, right? So your TCD here is, you see, we assume positive, right? And then the T3 is going to the left-hand side because you have your thumb to the left-hand side, and then T3 looks like that, okay? So this is minus, and this is positive, and then positive. So you see TCD plus T1 plus T2 minus T3 equal to 0. So after you move around, you have TCD equal to minus T1 minus T2 minus plus T3. All right. Again, if you are going to take a look at the torsion inside BC section, all you need to do, just do the cut. Cut it, and you find that T2 is still there, T1 is still there, and your TBC assumed to the right-hand side, and then TBC equal to minus T1 minus T2, no problem at all. And then AB section, cut it, you get TAB here, and then you have TAB assumed to the going to the right-hand side, and your T1 is still there, and then your TAB equal to minus T1. All right, so just very similar to what we learned in chapter 2, right? So you have TCD, TBC, TAB, and then shear force in each segment is TR divided by IP. So this T is supposed to be TCD, TBC, or TAB. Okay? And you have each shear stress. I should say shear force. This shear force in each section is this one. Sorry. Well, it should be stress. Stress. Okay, shear stress. Shear stress in each segment, all right? Stress. All right. And then your twist angle in each segment should be TL divided by GIP. Okay, and then each phi 1, phi 2, phi 3, phi 1, phi 3 will be, the total angle should be summed together. All right, so sorry, maybe I can give you more in each segment. So maybe I can give you like TI maybe, or phi I maybe, okay? Because I stand for section I. I could be 1, 2, 3, okay? Just like here. Okay, that's it. So I believe you understand this because this is very typical example we learned in chapter 2 in last few weeks. And then you can guess what will we see in the next page. Okay, again, you can see that it must be a integration, right? Integration for the gradual change of the cross section or gradual change of the torsion. Here, very similar. You see, this is T and this is T with the gradually change the section. Okay, and of course, the T is unique. Concentrated torque is pure. It's pure torque. And then you have d phi equal to T dx g IP. And you see IP here is a function of x, which means that the IP is actually changing through the x. Okay, so phi equal to do this. Yeah, just do the integration. No problem at all. And if you have another case like TA and TB, okay, and maybe you have different complicated torque along the bar, okay, so you should draw like this, TA, and you have Tx, right? So the Tx is function of x, so which means that all you need to do is just cut it, or you just cut one of it, and then determine the general form of the function of t, and then you can see what's the difference. All the change is only t become t, a function of x. That's it. All right. 这样应该蛮容易理解的吧？哈，就是说，如果你今天是这样子变化的话，就是截面积的变化就是在 IP 上面体现。但如果你今天是力量上的变化，也就是扭矩上的变化的话，你就要把每一个扭矩的，就是你的扭矩的函式要把它写出来，对于 x 的变化的函式要写出来。OK， 通常都会知道了哈，没有那么复杂，这样应该说题目都不会为难各位啊。好。So I believe this is quite simple because you learned that in chapter 2. So the concept is not new, okay? Right, so let's continue. So there is a shaft, okay? And there are three gears, okay? 3 gears. 齿轮, okay? And you have T3 looks like this, T2 looks like that, T1 looks like this, and here and there are 3, okay? So nothing fixed here, okay? And we are discussing the equilibrium state, stable state. So which means that this shaft is not rotating, okay? It's not rotating, okay? So let's take a look. D, of course, the D is the bar, right? Blah, 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 LBC, LCD, and T1, T2, and T3, okay? And G of the bar, yes. So find maximal shear stress in each part of the shaft, okay? So yeah, each part of the shaft. So only 2 parts, right? So it's a maximal shear stress in these 2 parts, okay? And then phi BD. So total phi, but between point B and point D. All right. So here, what does that maxima means? It means surface, right? You are going to determine the maximum shear stress. It must be the surface, and each part we only have 2 parts, right? 2 parts, BC and CD segment. Okay. segment. Right, so again, we are going to determine the maxima shear stress, which is tau equal to TR IP, right? IP. Okay, and it will be 16T pi d3. Okay, so what is tau BC? Tau BC, you need to determine TBC, right? What is TBC? And tau CD, we need to determine TCD, right? So TCD and TBC. All right, and all we need to do is just cut it, and leave the left-hand side, or cut it and leave the left-hand side, right? And I should move this to here, right? To make it, you know, align. Maybe you can see that even further, more clear. And then for the TCD part, because you leave the left-hand side, right? So your T2, your T2 still there, the T1 still there. But if you cut light blue, BC part, you only see T1, okay? And then you can just do the equilibrium. T2 minus T1 equal to 450 minus 275 equal to 175 Newton times meter. And TBC equal to minus T1. So minus 275 Newton meter. Okay, you see that TBC direction is wrong, right? Was assumed incorrectly, but it's okay. You know that. You know the system, so it should be fine. All right, so tau BC is 16 times 275 and pi times 0.033 equal to 51.9 MPa. Maybe you think, why is this not minus? It's okay, because we just want to know the maximum shear stress on the surface. But if depending on a different orientation, you may have positive or minus in the surface, but it's okay. We just care about the maximum value of that. All right. 就你可能会说，哎，这上面是负的吗？哎，对了，但是这边他没有在叫你画出那个stress element 嘛，他只在意就是说最大值是多少。那最大值，如果你今天看不同的面，你就可能会有不同的胜负号嘛，哈。所以这边其实他没有叫你画那个 stress element，真的那值就觉得就没有那么重要了，哈。当然，如果你要画 stress element，那就很重要，因为每一个面都有自己的 orientation，那这个正符号就要小心一下了哈。OK， 16 times 175 divided by pi times 0.03 cube 330 m pa. All right, so the second one is that second one. Phi BD equal to phi BC plus phi CD. Okay, so your phi BD and phi CD, your phi BD will be phi BC plus phi CD. Well, it must be plus because either phi BC is positive or negative. It's okay. Just sum them together and it will handle it by itself. Okay, so let's take a look. So you see now positive and negative is matter. Okay, I will give you a. So firstly, IP first, pi d4 divide by 32. And pi 0.034 4 divide by 32. 7.952 times 10 to minus a and 4. Okay. So let's take a look. Find BD. Oh. Okay, here. Phi BD can be equal to phi BC times phi CD. BC has what is that? BC is minus 275. Minus 275. Oh, so this here. Minus 275. So you can see that in the first problem, well, the values matter. The direction is not matter, right? That doesn't matter. Sorry, doesn't matter. But now you are going to determine the angle of twist, which means that it could be positive or negative, and then two sections twist angle may cancel each other, right? So the sign become important in the second problem. Okay, 80 times 10 9 2 7 7.952 times 10 to minus 8 and plus 175 0.4 and 80 times 10 9 7.952 times 10 to minus 8 equal to minus 0.016, minus 0.0106. All right, and it's minus 0.61 degree. Okay, that's the answer. So it's not really difficult. Yeah, it's not really difficult actually. The concept, especially. All right. Okay, so I guess, yeah, it's quite simple, right? And next, you are going to, you can expect it. What will you see in the next page? Orientation, right? I just told you, talk about when you talk about a stress element and then all the direction doesn't matter, right? Next one, we are going to discuss the stress element due to the torsion. Okay. Okay. Next one is easy. Well, again, proof in mechanics of materials. Proof. Next page is proof. We are going to prove or show the formula for stress on inclined sections. Don't you think that this is quite familiar, right? Very similar to normal loading case. Okay, so let's take a look. This is your stress element, okay, due to a pure load. Okay, pure load, you got the pure shear, right? Remember that? Remember, sorry, I need to swipe to the beginning of the here, right? Pure load, okay, pure load, you get the shear like this, right? Pure load, pure torsion. 纯扭，你就会得到一个中间的那个垂直的，就是这样子中心有一个方块的那种状态，然后它就是一个纯的 shear， 对不对哈？还记得这一页吗？哈 ，OK， so what we are going to do is that provided that, okay, in the case that we have a shear stress like this in the 0 degree, 180 degree. I mean, the proper square and stress element. And the positive X surface has the positive Y direction tau. So which means that this is kind of, positive stress element or the shear, okay? And you can see that this is actually in the, what we see here is a small element. It's a small element in the middle, okay? This one is this one, okay? And you see that this is up, down, left, and right. All right. So again, this is the enlarged version of this. Okay. This one enlarged. You can see this one. Okay. Now, don't you think this is a little bit something different from previous one? Is that this is going up, this way is going up, this way is going down, okay? So which means that your force, your torsion is actually here and here. All right, so you can see my hand is going to do that, okay? My right hand side going upward and left hand side going to downward. All right. And if I use my right hand rule, actually this tau is actually to this, right? So the right hand side, in the right hand side of the bar, the pink torque is going to rotate from bottom to up. So my thumb is going to the left hand side. Okay, how about the left hand side? Is going down to the bottom. So my thumb is going to the right hand side. All right, so these two things. Right, so remember this two thing is a little bit different from here, right? Because this is go kind of out, and then your shear is downward in the positive X. So this is actually minus shear strength, shear element. Okay, so be careful about when you applying this result. Okay, right. So now you got tau here, and provided that you have a tau here, and which is positive in X positive direction. All right. Then we are going to determine the component in a inclined section. Okay, the inclined section has its own x1 and y1, right? And this x1 has the theta to the horizontal, rotate about theta. Okay, so again, we do shear stress times area, and then do the force equilibrium, and then we can obtain what we are going to get. So let's take a look. We are going to cut a surface that oblique incline about theta. So these area, we cut it. Of course, this is theta, right? So this angle, just like this, right? So we cut it. So we cut it, and then leave the left-hand side, So we get the figure like this. Okay? So this is tau, what we see here. And then we can have the tau theta and sigma theta. Must be looks like that because the shear stress not shear stress, sorry, the stress status at this surface must either perpendicular to it or parallel to it, right? 好，这边要讲一下，就是说我为了要找到在 怎么讲，这个斜的这个面上的应力分量啊，我就把它切开来啊，切开来，然后留下左半边，左半边留下在这里咯。那这时候啊，一定这个三角形不会跑来跑去嘛，它一定是 equilibrium 的状态，所以一定会这边有一个 stress 的状态。那这 stress 可以画成两个分量，一个分量是平行于它的分量，一个是它垂直的分量，所以一个叫做 sigma theta， 另外叫做 tau theta。OK， 就这样。So if you can accept that, we can directly just follow exactly the same procedure we did before. Here is A0 because you see, you cut it here, all the area is still here. A0, no problem. And however, here is a little bit less because there's something here. It is not cut it included. So this area should be A0 times tangent theta, right? This is tangent theta. And this area is A0 times secant theta. Okay? So again, you have this area times sigma theta. So here are all stress, right? After you times the area, then you get your force diagram. Okay, so this one is sigma theta, anal section, secant. 我忽然不会念这个 sec 是什么东西 tangent secant OK 好 secant theta and this tau theta anal secant theta and tau anal tangent theta tau anal, that's it, right? Of course this is 90 minus theta, then all we need to just do the balance, easy. Okay, so now balance, we make the tau anal as a okay, so so I decompose the tau anal into two components. The first one is aligned to parallel to the this one, and the other is parallel to the inclined section. Okay, sorry, I need to move around for this. All right, and then you know how to do that. We decompose tau anal and tangent theta into two components. Okay, okay, so you know that how to balance the component together. So inclined normal direction is sigma theta anal secant theta, this one, and tau anal sine theta, and tau anal tangent theta cosine theta. Okay, so three of them summing out together need to be 0, and then sigma theta equal to blah 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 blah. And in plane direction. So this one and that one and that one. Summing out together, we got tau theta equal to blah 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 blah. Okay, easy. All right. So although it looks complicated, but you don't need to memorize it. All the procedures are so similar. Stress times area, and then become force, and then do the balance. Done. All right. That's it. And then you can expect what you will see in next page, because you have tau sine to theta, tau cosine to theta. You have sine and cosine, which means that you have maxima or minima. Okay, the maxima and minima. Next page, you will see really similar diagram. Okay, so in the pure pure torsion, if your focus face surface is this one, and which means that your theta equal to 0. So you have tau maxima and 0 normal, because you are undergone a pure torsion. Okay, no normal stress. And then you have your own 90-degree phase tau, and you will give your tau become negative maxima negative. Okay, so you see in this, again, your neck need to be broke a little bit. Okay, twisted. You see this pink. You see this pink. Okay, this is 90-degree and positive x1 direction, but minus y1 direction. So this should be tau, should be minus side. You see, this is minus. Okay, so now you can see that how the value corresponding to the diagram. Okay, and 45-degree. How about 45-degree? 45-degree here corresponding to maxima shear sigma theta, which means that you have maxima normal stress at 45-degree and no shear stress. Okay, you only have a sigma theta at the maximum, and the value very lucky. Okay, sigma max at 45-degree just equal to tau value. 很有趣哦，就是当你在45度，在你纯扭的状况下，在你的45度角的地方，你就正好45度角那个方向是没有剪应力的，但是你有最大的正向应力 sigma max 在45度角的地方，而且那个 sigma max 最大的正向应力的值，正好跟你的 tau 是一样的值。虽然这样看起来好像 sigma 等于 tau， 这样，哎，你在讲什么？就是为什么正向应力会等于剪切应力？这样不对吧？没有，这是值而已哈。如果你学过那叫什么程式语言，大家就知道是什么意思了哈。就是这个 tau 只是一个值，一个变数名称而已哈。tau 等于，例如说20的话，那 sigma max 不就是20？但不代表你的剪切应力就会等于垂直应力。就它的意义不一样啊，它只是值刚好一样而已。Okay, so that's it. And you can notice that what it tell us, a material with weak tensile strength will break along 45-degree. Okay, so you can see that if you have a concrete bar, concrete is good for compression. So you can see that the concrete, why we can make it a column, we can stand on it because it is good for compression. How about if you kind of, make it tensile? It will break because concrete is very difficult for tensile. How to generate tensile? Earthquake. If you have earthquake, so your column will do like this, right? And when you do this, and here become tension. So you can imagine that you do this, right? And then this band is going to stretch tensile. So column also do that. Dun, 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 and here is longer, and then it will break. All right. So, or if you do the twist, you will have 45-degree crack in the material. All right. Right. Yeah, talk about the earthquake. We can see the very horrible news in Bangkok, and you have we can see that there's a big building and it crashed down in seconds. That's really bad, and yeah, that's really terrible. Although this building is under construction, not finished yet, so we cannot blend that to, we cannot blend that. It's just bad luck, but still, it's really difficult and horrible. And interestingly, that we are thinking. I was thinking. Do you know? I mean, I was wondering why house or building in Taiwan are so expensive and compared to the house in America or US. I have a friend. I lived in US for 8 months, like 2 years ago, and I know that the price of the house in US, you have like we have similar price, but if we pay similar price in Taiwan and US, in US you will get a really big house, all your own, stand alone, okay, and then you have your garage and the garden, backyard, very big, very beautiful. But in Taiwan, you only have tiny rooms, and so I'm wondering why. So I conclude two reasons. The first one is that US is big, very big, very, very big. So the the density of the population is lower than here, so cheaper, understandable. The second thing is that I examine those house, because the house only have one floor, so all the column or the beam are made by woods. Okay, so the woods, so it's kind of weak. But in Taiwan, we because the density, so population density, so you need to build up the high level of the building, and then everything become, you need to be concrete, and also we have earthquake, so we need to be strong, earthquake proof, right? So the technique and skill of the building must be really good. Okay, so I would say engineers in Chinese, sorry, not Chinese, in Taiwan or China or Japan, maybe, yes, because we have earthquake, so we are more, better than those in US. Yeah, so that's the reason why our house are more expensive. But of course, we need to considering politics or bad things in Taiwan, Ghost Island, right? So 听得懂吗？总之就是我那时候在想，为什么我去美国8个月，然后就看他们哇，那个我朋友买了一个房子，就大概1000万左右，然后是一个哇超漂亮，然后就是一栋房子，然后很大，然后有前院后院，然后很漂亮，车库超大的，1000万，然后我们这边1000万就是买一个小套房这样子。那我后来就看他就很平房，他就是独栋嘛，所以就只有1楼而已，然后又不会有地震，所以它的柱子啊什么大部分都是木头做的。那我想到那当然那就是便宜嘛。但是我们这边的话就是很密集度很高，然后你要盖得很高，你盖得很高又有地震，哇，那你就是要耐震啊，什么都要弄得很好，你的技术要变得很高，所以技术面就很高，需求很高，所以难怪就是很贵。哦，当然了，比如还有很多其他的因素啊，政治啊，或者是炒房啊那些那个我就没办法了。但是本身这个东西本来就是比较贵，这就是比较难。哦，在这边我们做事就比较难，所以这也造成我们 我们的工程师啊，就是比较强，很强，像日本的工程师啊，台湾工程师都很厉害的。再跟大家分享一个很有趣的事情，哎，是不是要下课了？最后3分钟，好，那就反正都拿了一下，最后3分钟就跟大家来，就是我小朋友那时候才3岁，然后我们跟大家讲，我3岁，我就带他去跟我的朋友，我的朋友就是在那边当教授，所以他的小朋友就是美国人，好，然后呢，他也是3岁，所以我的小朋友跟他就是跟他的小朋友是可以玩在一起这样。然后有一天我们跟他出去，结果我就发现，我不知道我们讲过这件事，有没有走楼梯的事情啊？没有，好，就是说啊，我们就到了一个地方，就是比较像是，因为我们就是4个人去，我应该说，我跟那位教授朋友去参加研讨会，然后我还带着小孩，我跟他都带着小孩，所以有4个人啊，就一起去研讨会，然后我们就住一个比较便宜的，反正我们想说啊，4个男生就住比较便宜的，就是算是那种汽车旅馆嘛，就是美国那种比较 low 的那种旅馆，不是那种饭店，所以我们要走楼梯哦，走楼梯就要上第2层。这时候我就发现我的小朋友就这样噔噔噔噔噔3岁噔噔噔噔就上去了，但是我的朋友的小朋友就是这样，然后他爸爸就牵着他手这样。我想说3岁为什么要3岁都可以很容易的，就是咚咚咚上楼梯啊？然后我想说为什么会这样？后来就发现，因为他们的美国的地很大，他们不需要盖2楼，所以他们全部都是1楼。所以我们家我们家住在4楼，所以我们3岁小孩1、2岁就开始自己上楼梯，但是他到3岁，因为没上过楼梯啊，所以他就有点难。然后再不然就是，如果是 shopping mall，哎，也有那个电扶梯，所以他们很少训练走楼梯。所以我想，哇，这个真的是民情。还有另外一件事情是，我的小朋友去那边8个月，当然就稍微的习惯了那边的生活。在后期的时候，我们在开车开在路上，然后这时候我的小朋友就看到外面说：“哎，爸爸，外面有人在走。”哎，我整个就 shock。但是真的很奇怪，外面真的有人在走是很奇怪的事情，因为美国实在太大了，所以通常大家都有车子，所以如果你看到一个人在那边走，不好意思，他可能就是，除非他是穿着运动衣在那边跑步，你可以看就比较 reasonable，不然的话，不好意思，通常都是 homeless，就是他就没有车，就只好走在路上，然后就是会，对，就很辛苦。所以通常真的还蛮夸张的，就是你可以发现地大跟地小的那个生活形态是完全不一样的，然后造成我的小朋友到最后就是价值观很怪，哎，他怎么在路上走路这样？而且他们大到就是说他们通常都会有一个区域是商店嘛，哈，所以就是例如说邮局在这里，然后麦当劳在这里，它就是一个很大的区域，但是旁边都有很多店嘛，然后中间就是停车场，对不对？哈，那我们认知就是说，如果我今天要办完邮局，要去吃个麦当劳，我们就是停好车去办完邮局，去麦当劳，对哈？他不是哦，美国人都是开到邮局，然后再开过去，在同一个停车场开过去，然后就吃麦当劳。哇，真真的很棒，这是一个很舒服的国家。啊，That's it. OK. America is good. USA is good. Done. 好了，下课结束。啊，有什么问题来问我，谢谢。问，好，一个马牌。哦，PB，因为 PB 是不是因为你的 PB 这边是往下嘛？哦，都是在。诶，对啊，负20，这边是往下的，对不对？
你要说就是最后因为是负的最长，它一开始
对对对，它是往上，那所以它这边我算出来这一根来说，BD 来说它是往下，对不对？哈，那但是这边往下 B 点跟另外一个垂直的 bar 要合在一起，那合在一起的时候，这边往下的时候，这边就该往上，因为它 B 跟 B 合在一起的时候，它必须要抵消，所以说这边往下，不好意思，这边往下，这边就要往上，所以这边是 PP 加上，对，所以它是上的，所以它就是这边是22.3，这是22.3，所以这不是负的，是正的。对对对对，嗯，因为它加在一起就变内力，嘿，不然的话，如果它没有抵消的话，你就会在这边看到一个多出来的力。嗯嗯，OK，好，谢谢。这样是不是代表我 OCW 没有讲得很清楚？那我就表，这就是这样啊。你看那时候，对，就是教完以后开始教英文的，反而对，反而就会更清楚。但是我还是会进步的。 刚刚有超过1分钟下课，所以就还各位1分钟吧。好，你知道我从以前当学生的时候，我就非常讨厌老师晚下课，所以我进当老师的时候，我就很少拨时间。怎么样？不错吧？对，我就很讨厌那种啊，明明就，嘿，就是我蛮可以理解的哈，就是我当然很想要把刚刚东西都讲完，告个段落，但有的时候就不差那2分钟嘛，对不对？但我偶尔还是会这样子啦，哈，就可能超过1-2分钟，但我只要一超过2分钟，我就会很焦急，就是好，我不能这样子，我不能这样，所以对，anyway，知易行难啊，所以要把时间控制好，其实是一件很很难的事情。你知道我小时候啊，忽然要开始讲以前的事情了，就是呃，我小时候就是会被国小的时候就会被老师说，哎，周文弟你去参加演讲比赛或是朗读比赛，然后你就要控制时间，所以就是现在算是身经百战了哈，所以还上台讲话还算是有经验哦，对，所以这个是，然后小时候就觉得我很可怜，就是别的小朋友都可以出去玩打球，但我要去练演讲，我要去背讲稿什么什么的，然后我就要去正音，正音班，对，不过还蛮有帮助的，对，当然了，如果我当那个就是我的职业不是老师的话，那这样以前就好像没什么帮助嘛，对不对？不过真的以前小时候学到的东西，真的是对于长大不知道哪个地方就会有用，这样，嗯，很有趣的。Anyway, let's continue. All right, so strengths and pure shears. Okay, tau equal to G gamma. So this is Hooke's law, right? This is Hooke's law, and then the previously it was a square shape, and now it become a shape like this. All right, and you can see that it should be uh, okay. Previously it should be 90-degree, half pi, right? But now it is gamma over 2. It's gamma over 2, gamma over 2. All right. So it has the gamma over 2, gamma over 2. So in total, the gamma is the shear strength, which is the change of the angle of the element, right? So you can see it looks like this, all right? Tau, 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 tau. So it make it shape like looks like this, 平行四边形, all right? Or you can see that if you change your element become 45-degree, you can see pure normal, okay, sigma mix with tau, and sigma minimum equal to minus tau, okay? So compression and elongation at 45-degree and minus 45-degree and 135-degree. Okay, so you can imagine that this square become a rectangular shape. Okay, so you can see that epsilon mix in this direction. Epsilon mix in this direction is actually sigma mix. Sigma mix divided by E, which means that tau divided by E, because sigma mix equal to tau, all right? So this is the first term. So you can imagine that the epsilon mix along this direction. How about I make it this axis? All right, sigma max in this axis has two contributions. The first one is caused by tensile, all right? The other is this one is compression. Compression, side pressure. Well, it's not side pressure, it should be compression. You can see that this is actually direct translation, Chinese English, Mandarin English. Well, compression. 你可以看到压力直接被翻成 pressure， 但不对，它应该是 compression 才对。Compression, caused by compression. Okay, and the compression is tau divided by E, but the tau is minus, and minus times the Poisson ratio. This is Poisson ratio. Poisson's ratio. All right. So when you compress by lateral, you will have an axial elongation. Okay. So tau divided by E is tensile, no problem. And this is done by compression. And compression has minus sign, but because the nu here is minus sign, has minus sign as well, then you can have tau divided by E times 1 plus nu. Okay, so epsilon mix actually become this one. Okay, 听得懂吗？有两个共线，一个是拉长的共线，一个是旁边压的时候会补松比的，到这边让它更长一点点，这样子有两个共线，然后把它写出来以后就变成这个东西 ，epsilon mix 等于这个东西。Okay, you can imagine that if you have a pure shear, your 45-degree well has the epsilon strength, tau divided by E times 1 plus nu. Okay, what will it, I mean, why we are going to looking at this? Did you notice that the tau can be related to G gamma and your E here? So next page, we are going to correlate G and E. Remember in the first few chapters, I said G and E are correlated. And then I said, I will prove that later. Yeah, here it is. Okay. Now, so now here is a typical square. All right, typical square. You have A, B, C, D, and the square has height h and width h. And then you notice that this BD is square root h, no problem, right? And then if you have a pure torsion, so you have pure shear here, and you get the, this shape, and this line should be elongate, right? And what is elongation? LBD. The LBD here, the new LBD. So we take this angle, this triangle here. All right. So BD becomes LBD. Okay, which is longer than square root 2h, right? It's longer, okay? Longer than that. And here is this angle here is half I plus gamma, no problem. And the h, no problem. And here's pi over 4 minus gamma over 2. And here again the same. All right, so we can use cosine theorem. 叫余弦定理嘛，哈。Okay, so cosine theorem, LBD square equal to H2 plus H2 minus 2H2 cosine pi over 2 plus gamma. Okay, so this angle here. Okay, so you can see that LBD. What is LBD? LBD is the length after the displacement, after the shear. So square root 2h should be related to this LBD by epsilon max, because epsilon max is along this direction, right? 45 degree. So you can imagine that LBD equal to square root 2h times 1 plus epsilon max. All right. So this one, I believe you understand this. So I substitute this LBD here. I mean here. All right. All right. And then you can divide square root 2h. And then you can have 1 plus sigma epsilon maxima 2 equal to 1 cosine minus cosine, blah, 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 blah. Okay. Then we can continue. We expand this. We can get this one. All right. And something we need to see that, so minus cosine half pi plus gamma equal to sine gamma. All right. So if you can understand this, then this one we can using the assumption in mechanics of material that epsilon max is small. Okay, and gamma is small too. All right, so the higher order term can be negated 0, and sine gamma become gamma, because remember that sine and tangent gamma, if gamma is small, the sine and tangent gamma are approximately become gamma. Okay, so you can have 2 times tau times 1 plus nu divided by E equal to tau over G. Of course, this one epsilon max. Okay, epsilon max. We obtained in previous page, right? Then shear strength gamma here, we can substitute here, so we can get this one. All right, so we substitute here and we substitute here, we can get this one, and then we can get G equal to E times E over 2 times 1 plus nu. So that's the relationship between E and G. Okay. And interestingly, well, we can also think 2G equal to E divided by 1 plus nu. Okay, what that for? We just continue to substitute this here. Do you see that this part are quite similar, right? So you can see that we can further make the epsilon mix even simpler. Okay, tau divided by 2G. So tau equal to gamma over, no, tau not over, epsilon mix equal to gamma over 2. All right, so we obtain new informations. Epsilon mix equal to gamma over 2. Okay, 好，这边我觉得蛮重要的哈，我们把前面的那个斜线式十五角 epsilon max 写出来了哈，长这样子对不对哈？然后我们那时候不是说 E 跟 G 有关系？哎，这边前面又有 tau 可以用 Hooke's law 跟 gamma 跟 E 有关系，G 有关系，所以我们就发现，哎，这是一个好机会把 E 跟 G 联合在一起的方法。好，那这时候我们就开始看了哈，哎，这边这个 proof 啊哈，真的是材料力学里面我少数不是用 stress 乘上 area 的哈，所以这个需要想想哈。好，你就看到原本它是根号 2h 的长度，结果经过纯扭变形以后，它变成 LBD 这个长度。然后呢，我们 LBD 又可以用余弦定理去把它找出来的一个关系式写成这样。那 LBD 是变形后的长度，所以你可以用原本的长度乘上1加 epsilon max 嘛，因为它是45度角的方向了哈，所以你就可以把这个 LBD 替换掉。然后算出来以后呢，我们再利用展开以后呢，我们再利用 epsilon max 跟 gamma 都非常小的状态下，我们去除微小项跟把 sin 跟或 tangent 的 gamma 哈，把它简化成 gamma，就可以得到这样子的式子。那当然就把这些都带入进去了哈，把这些都带入进去。好，带入进去的话，达到这个是 G 等于1除以2括弧1加 nu。好，这个东西我们就证明出来了哈，就那时候说它们有关系是这样子，证明出来了，很棒。好，那这时候又多一个多一个 information 啊，多一个资讯，我们就把它这样稍微这样移动来移动去，因为我们发现 epsilon max 有这个地方长得很丑嘛，对不对哈？哎，我们可以用 G 来代替，我们就把这个东西 G 来代替，就 G 跟 tau 又弄出来变成 gamma 哦，所以说 epsilon max 其实等于2分之 gamma。等一下我会用到 ，we will use this new information later. All right. So during the pure torsion, your epsilon mix will occur at 45 degree, and epsilon mix will equal to the value of the epsilon mix equal to gamma over 2. All right. Now, next one, I believe you will understand what I'm going to determine because we are going to draw stress element due to the shear, due to the torsion. All right. Next one is what we're going to. I guess you will foresee or predict what coming up next. All right. Next. This is a tube. This is a tube. All right. And this is the problem, looks like. So T equal to 4 kn. G is a material property. D out, D in. Okay, no problem. And you need to find tau mix, sigma T mix, sigma C mix. What does that mean? Which means that the T here is tensile. Okay, and of course the C here is compression. Compression. All right. And show these stresses on sketch of properly oriented stress elements. Or I mean, just draw the elements and then at that direction. Okay. And then the second problem is epsilon T mix and epsilon C mix and draw the deformed elements. Okay, so you are going to, so second part, and I mean, yeah, I can show you how to draw this. Don't worry about that. Now, so after the T, you can imagine that the T, if you're using your right hand thumb, so the right hand side, you have the up or up to the down. So right hand side up to the down, and the other side will be bottom to up, bottom to up. All right. So if you have a stress element at the middle, okay, you will have right hand side down, left hand side up. Okay, and shear is coming in pairs. Okay, so based on this loading condition, you will know that in the 0-degree orientation, it has negative shear because it's positive x direction, but minus y, positive x surface and minus y direction. It's kind of minus. Okay, so this minus shear element. All right, so let's tau mix. What is tau mix? Tau mix equal to TR, right? IP. This is R. R should be the radius, right? So 4,000 times 0.08 divided by 2. And IP is 0.08. 4 minus 0.064 pi over 32. Okay, so equal to 58.2 MPa. All right, so you have 58.2 MPa, and then yeah, because you have a highest tau in the pure torsion case, right? So let's draw the shear element, stress element here in the maxima shear case. So it will be down 58.2 MPa. Okay, and right hand up. Left hand. So you can see that this is exactly what it looks like here, right? And then and every point is 58.2 MPa. 58.2 MPa. And 58.2 MPa. So that's the maxima shear stress occurred in this bar. And at these four orientation, 0, 180 degree, 270, and 180, 270. All right. Next, what is the sigma C max? Sigma C max. Right. So actually, well, wait a minute. Let's take a look. Sigma C max or sigma T max. Right. Actually, we don't know it yet. All we need to do is going to determine the sigma maxima, but we are not sure the direction. So let's try. We know that sigma theta need to be 45 degree or 135 degree. Okay, so let's try sigma 45 degree. Okay, well, I should say theta equal to 45 degree. All right, so tau sine 2 theta and equal to, okay, this is quite 58.2 minus. Be careful about this. The reason why here is that your tau is in the 0 degree, right? The 0 degree here is minus. All right. So need to be careful and sine 90 degree. Okay. So it become equal to minus 58.2 MPa. Okay, so you see This is a minus, right? Minus. So I can say this is compression. Okay, so actually I didn't know this one is compression or tensile, but after we done the calculation, we know this is minus. Okay, this is compression. So the other must be tensile, right? Tensile. So tensile sigma theta equal to 135 degree. And tau still be equal to tau sine 2 theta. Sorry, sigma t equal to tau sine 2 theta and minus 58.2 sine 2 times 135 degree equal to 58.2 MPa. This time it become positive because sine 2 times 135 degree become minus. Okay, so minus minus become positive. So it's feet tensile. All right, so now we are going to draw the element. Okay, this is 45 degree. So hope you can see that. 45 degree. X0. All right. Then, so 45 degree compression, right? Compression. And 135 degree is tensile. All right. So it should be 58.2 MPa. 58.2 MPa. And 58.2 MPa. And 58.2 MPa. Okay, that's it. So you can see that maximum shear stress happened at 0 degree form, and 45 degree shear stress stress element has the maximum compression, the maximum tensile. Okay, so that's the first problem. And the second one, epsilon tensile max, epsilon compression max. Okay, so it wants us to draw an element after the deformation. Okay, right. Oh, well, before I do this, I also want to give you extra information. All right. How about this one become, this is stress element. What is the deformed element looks like? 就是这个东西是最大剪应力发生的这种状况，对不对？好，但是经过它这样子剪力运作在上面的话，它的元素会长成什么样子呢 ？OK， 那长成什么样就是 deformed 变形的元素的长相。OK， 那这时候你可以画两种状态。There are two solutions for this. So you can imagine that this is going to become like this, right? So you can either draw like a, let me take a look. So this is before the deformation. Before, okay? Let me copy. Okay, so this is before. And you can have two, when you have the test, you write down your exam sheet. You can either draw like this. Okay. And this is gamma mix. Gamma mix over 2. Gamma mix over 2. You can draw this. This is, I think this is more, this is the most reasonable plot, because you can see there are 2 force here, right? 2 stress here. So you're kind of doing like this and doing like that. Okay, so just like very straightforward. Okay, or you can make it lie down on the surface. You can do this too as well. No problem. Okay, and then you can say this is gamma mix. Both are okay. All right. Well, although it looks really different, but actually you can remember the gamma mix is really tiny, really small. So actually you cannot tell in the real world, you cannot tell these two different. Yeah. Okay. But when you draw the figures, when you're writing the test, both of them are okay. Okay. So, right. That's it. So this is the first one. First one. All right. How about the second one? Second one is that epsilon T maximum. So because we're going to get epsilon mix, right? Because it tells us epsilon T mix, epsilon C mix. So epsilon mix is actually equal to gamma mix over 2, right? Which is 0.0011. If you forget what I'm talking about, I give you a pink highlight, and then you see the same pink highlight here, right? In the previous page. So pink highlight here. Epsilon mix equal to 0.001. 0.0011. Oh, and wow, sorry. I make it too quick. I jump a little bit. Gamma mix equal to tau mix divided by G. Okay, so it should be 58.2 times 10 to 6. 6 divided by 27 times 10 to 9, provided in your problem, right? And then equal to 0.0022, which is in radian. Okay, so in radian. So your gamma mix divided by 2 becomes 0.001. Okay, so now you are ready to draw the deformed element. Previously, it looks like a 45 degree, right? 45 degree before the deformation. After the deformation, you see in the 45 degree, it compress, and in 135 degree, it elongate. So I will make it, it compressed and elongate. That's it. And oh, I should emphasize that this surface, so this surface should be 45 degree. 45 degree. And this is the x, and this is the x1, right? And here is epsilon mix equal to 0.0011, and the other is, sorry, epsilon max equal to 0.011. Well, they should look exactly the same length. I should make it shorter. Okay, that's it. So that's the deformed element looks like. Right, that's it. Normally, I should share some interesting story now, because there are many things you need to draw and note. I need to think about what should I share.嗯嗯，不知道讲什么。在美国的事情吗？在美国的事情，我只能说美国的空气跟天空真是美丽啊，就是他们夕阳就很漂亮，天空都很蓝，真的是。然后我们的台湾的天空都是灰蒙蒙的，我觉得很难过，真的是，唉，人家然后偏偏人家又那么多排碳量，对不对？为什么我们就这样？我就觉得很不开心，就有点那种就是小时候不是一个那种班级里面就有些就是不好意思啊，就是家境很好跟家境不好，你就会觉得说我们台湾人的这种家的境环境是没有那么好，真是蛮难过的，唉，但是啊，但但我必须要跟大家讲哦，我真的觉得台湾人的平均的智商是比较高的，这是真的，我真的觉得，因为我在我身边看到的就是你们嘛，还有我以前的同学，我都觉得他们都超聪明的，你们也超聪明的，但是我去了英国啊、美国的那些名校啊什么的，他们就发现，他们也不过我们都觉得哇，他们都很强。当然了，MIT 真的很强，每个都很强啊，我知道。但我是说那些普通的名校，我就觉得也还好。然后甚至有些觉得哇，你怎么进得来这种？所以我真的觉得大家真的都是非常的有天分的，好，那都很聪明。然后台湾人，我真的觉得脑袋智力是非常平均起来是非常厉害的，所以大家不要妄自菲薄。虽然环境不是很好，但是也是一种磨练的哈。Anyway，下一页，共勉之。In English, Taiwanese is smart. Okay. 好 Okay. Next, I'm going to talk about the power. You know power, horsepower. Remember that? 马力, right? Sometimes we will say, oh, this car has such how many horsepower. Actually, it is talk about the uh, energy, the power, the energy which can deliver or work delivered by the shaft. Okay, so you can see the motor-driven shaft rotates an angular velocity omega. Angular velocity omega is actually radian per second. No problem. This is a angular velocity. No problem. The work at W done by the torque T on the shift equal to the torque T multiplied by blah, blah, blah. Actually, very similar to the work with the pushing. You have the force times displacement. You have torque times angle. That's it. Very similar to what the system you're familiar with in your senior high school, right? And assume the torque T remain unchanged. The power delivered by the system, P watts, which is P divided by dW divided by dt. Well, so you can see that the power is actually how efficient the energy, the work into that system, right? So into that, maybe the cars, okay? The motor into the car. So your power P is dW over dt. And then the W equal to T, fine. So if the torque remain the same, so T times this one is omega, okay? So the relationship between frequency and angular velocity. What is frequency? Frequency is how many round in 1 second or or per unit time. Okay, how many round? Okay, so you can see how many round is 2 pi. 2 pi. 2 pi is radian. Is radian for 1 round. Okay, the F is how many round each second. Or you can say unit time. Okay, that's it. So your omega is radian for 1 round. How many rounds each second? So omega here. So P time equal to T times omega. That's it. So power in imperial unit was what I mean. 哇，帝国 imperial British phone, UK phone, 英国 okay, horsepower 马力 but well in American or something you can use watt, right? So 1 horsepower blah 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 roughly equal to 746 watts. Okay, now I mean this is just a terminology, definition of terminology is not really important. But all you need to do, I mean, you need to understand what is concept of it, and maybe you can be a F1 racing car designer or something, engineer or something. Anyway, so there is a motor here, and then has a shaft as the diameter d, and you rotate with omega frequency, and the tire provide torque T here. Okay, so the power P equal to 30 kW, and tau allowed is 42 MPa in this blue bar. Okay, so the require of D, if the frequency is 500 RPM. What is RPM? Round per minute. Round per minute, or RPS, round per second. And you know how to transfer this, right? Easy. Okay, so there are 2 problems in this example. The first one is 500, the other is 3000. Okay, so you can see that the frequency increased in the second problem. All right, and we need to design the shaft, otherwise it will break. Okay, so tau mix equal to TR over IP, right? This is what you learned before, which is 16T pi d square, and P equal to T omega equal to T times 2 pi F, which is T equal to P divided by 2 pi F. So the first one is 42 times 10 to 6 equal to 16 pi d3. And P times 2 pi F equal 1630 to 3, 10 to 3. Pi d3 2 pi 500 divided by 60. Okay. So d3 equal to 69.5 times 10 to minus 6 m3. So d equal to 41.1 millimeter. All right. I mean, this is just substitute all the value into the formula provided in the previous page. Not very big deal. And the second one is 22.63 millimeter. So you see that higher speed, require a smaller diameter. Okay. Under the condition of the same power and allowable stress. Okay, that's it. Higher speed requires smaller diameter. Otherwise, it's more difficult to rotate, right? Okay, I guess that's it. And next week, we will finish this. 1, 2. Yeah, we'll definitely finish it. And then we are going to entering after 1, 2, 3, 4, 5, 6. Only 6 pages left. So next week I will finish 6 pages and into chapter 4. Okay, the chapter 4 is really important because I will say chapter 5 is the most difficult chapter in this course. And if you don't know chapter 4, none of the problem can be solved in chapter 5. You need to use the skill you learn, a knowledge you learn in chapter 4, and then you can solve the chapter 5. Okay, so chapter 4 is really important. Okay, and yeah, chapter 1, 2, 3 will be your midterm 1 range. Range. Okay, so I guess that's it. I will see you next week. Tomorrow you will have a holidays, right? So enjoy and prepare. Okay, thank you. Bye.